to fractional MeV energies. So again, for the recording, nonlinear processes in plasmas that drive superthermal electrons to fractional MeV energy. So normally we're thinking in laser-produced plasmas, which is mostly what I'm talking about, which are hot and dense. The lasers are producing some temperatures in the hundreds of eV for the general thermal continuum, and maybe some line emissions in that same region, but perhaps up into a few kilovolts, not much more than that, and rapidly dropping. So you might get up to 3-4 keV, but the emissions is dropping quickly, and there can be both continuum and line emissions. But if the intensity is high enough, as you'll see in the coming slides, you can get whoppingly high energies. So let's have a look at where do these come from. So from an analytical part of this, and this is an example of where analytic techniques are really helpful in understanding the process. You use simulations for sure, but they're limited in the number of particles, et cetera, et cetera. So this is Maxwell's equation. This is the fluid level plasma equation. So Maxwell's equations and the continuity equation, conservation of particles or mass, and the momentum equation, known as Navier-Stokes if you had a viscosity term in here, which we don't have. Okay, and so what's the boxes are outlining, and I think these boxes got lost, as I recall, in the text, but they're in the errata. What they're outlining is where there are product terms, which would allow some nonlinearity. So this is J, the current density, NQV, and N can vary and V can vary. And if you have an intense laser coming in, it's certainly going to drive the velocities to high amplitudes, and that may affect the density. For instance, this would be where there would be a three-wave process where the incoming wave is driving the velocity in the plasma, and it's producing an electron acoustic wave. There's a density variation, or an ion acoustic wave, both happen. Okay, and in the continuity equation, there's the divergence of NV, so that's another product term, same product. Okay, and in the momentum equation, you got lots of nonlinearity. So here there's a VV term, okay, in the substantial derivative. And then in the Lorentz force term, you have N times E, so there's a product, and then you have N times V again. So these are where some of these nonlinearities are going to arrive. The next slide.
Professor?
Yeah.
So when we're looking at those nonlinearities, is that typically like perturbation theory level nonlinearities, or is it much greater than that for these plasma processes?
So what you often do is you do a perturbation analysis to see initial growth rates, but that's all you get. After that, you have to switch to simulations. Okay. So for instance, here, you might say, well, the density variation is small. You know, you write the density as N0 plus N tilde, where N tilde is very small, and V is maybe that's a more dominant term or something like that. So you do that, but of course the perturbation methods only get you so far, but they could be extremely valuable. They give you some insights as to what the parameters are that you could control and stuff like that. Yeah. So this one, I'm going to show you this a couple of ways, but I wanted to bring it up because earlier maybe 2 lectures ago, there was a case where I didn't like the way basically the conservation of energy and conservation of momentum, putting H bars on everything. I didn't like the way they appeared in one of the slides, and I realized afterwards what the issue was. Actually, the slide was just fine. But basically, this is saying that through the current density J, which you can represent in the usual way, okay, you have some incoming wave, and perhaps it not decays. You could say it decays into 2 other waves, but if it's strong enough intensity, decays isn't the right word. It's more like evolves, okay? But if you analyze, if you say, okay, this is the current density J, then there's a relationship between the amplitudes, and there's a relationship between the frequencies, and there's a relationship between the wave vectors, and that's the only way you can have an equal sign satisfied. So that gives you these frequencies, and then we often put H bars on them to make them conservations theorems. But the comment here, and this is where I slightly misled you, is that there's a linear scattering and there's a nonlinear scattering. And these relationships can be written and are written differently for the two. What's going to happen is the indices 1 and 3 will switch. What you have is you have a three-wave process. And if you make the vector diagram, how you read these relationships depends on which way are the arrowheads on that vector diagram. So I'm just going to show you something we've looked at before and clarify this in a couple of slides. And it'd be great if someone makes comments along the way. So this is one from chapter, I think 2 or chapter 3, chapter 2 it says, where we did the same thing. And we wrote the current density, etc. And we said that this incident wave comes in this case, it was purely linear. There's a wave here, and this incident radiation scatters off that wave and goes in some new direction. And the three together satisfy these relationships, okay? So it's saying that the scattered wave, this one, let's say the vector-wise, is the sum of the incident one and this one. And one of the examples I gave you was Bragg scattering from a crystal, where this is a stationary distribution of charge in the crystal. And so the incident radiation comes in and scatters off it. Because it's stationary, there's no frequency here, which means that over here, there's no, omega d is 0. So omega s and omega I are equal. The two frequencies, the incoming and outgoing, the frequencies are equal. And if that's the case, the amplitudes of the k vectors have to be equal, which means that this has got to be an isosceles triangle. The magnitude of ki and ks have to be equal because they both have the same frequency, okay? So this is the vector diagram. And from this, you get Bragg's law for a crystal. And so that was a case where this was not a particularly intense radiation. It's just a probing X-ray. This was a stationary crystal. This is the outgoing wave. So in that case, it's the outgoing wave that we have on the left here. K scattered equals K incident plus K despacing. That's what that's meant, or periodicity D. So that was one case, again, where the outgoing wave is on the left here. But in the nonlinear processes in the plasma, it can be different. And now we can find a case where the incoming wave is very intense. This is omega I and ki, and it evolves or devolves into two waves. A plasma wave, which it brings up out of the noise. There might have been fluctuations with that frequency, but they were in the noise. But this incoming wave brings it up, simultaneously scattering off it so that it's always satisfying these relationships. And in this case, what's on the left is omega I, and omega S is on the outside. So it's just a matter of how you arrange, as I said, the arrowheads on the vector diagrams. So this is a correct relationship for the decay or devolving of the intense incident wave into two other waves, okay? So here's the omega I on the left, and here's the omega S on the left. So both are correct, just the application. Any comments on that? Okay, so here's I'm sorry, yeah, go.
So like to clarify, when we have our incoming radiation being like intense, that's when we tend to have like this de-evolution of the incoming ray. Is that kind of what you're saying?
Yes, exactly. Yeah.
Okay.
Yeah, these two waves they both have to be there together. There is a three-wave process, and it only works that way. And this is the vector relation. These are the energy and momentum equations. So then here, specific to plasmas, here are two processes. Oh, and by the way, these things are called stimulated processes. So where the incoming wave stimulates this plasma wave to come out of the noise and then scatters off it, this is called stimulated scattering. This incident wave is stimulating the other two to come up out of the noise and to scatter off them. So here are two really common or well-known examples of stimulated scattering. One is called stimulated Brillouin scattering, and one is called stimulated Raman scattering. So if you're familiar, Brillouin scattering is historically the scattering of light off sound waves, where the sound waves are quite low frequency. So this is, in the plasma case, they use the same name because it's like Brillouin, but rather than be a low frequency sound wave, it's a low frequency ion acoustic wave, okay? And the stimulated Raman, well, Raman scattering, Raman got the Nobel Prize for shining light into a gas and having light scattered out of it, which had a really big change in frequency. And it was because of resonances in the atoms or molecules that he was illuminating. And so the incoming wave was a light wave, and the outgoing wave had a really big shift. It might have still been a light wave, or maybe it went into the infrared, but it was a big frequency shift. So so in plasma physics, they use the phrase stimulated Raman when there's a big change in frequency, and that would occur when the wave that gets stimulated is an electron acoustic wave. So in the Brillouin case, it's a low frequency ion acoustic wave, and in the Raman case, it's an electron acoustic wave, which is at more or less it's at the plasma frequency. So that's why there's a big shift here. Okay, the relationships here. This is one where we're devolving from the incident radiation into the other two waves. And these are the vector relationships that occur in both cases. And I'll just look at the one, let me say, in the Brillouin case, this is such a small frequency shift that the magnitude of the other two waves, the vectors, pretty similar, okay? Because the frequency shift wasn't very much. But in the Raman case, the incident wave frequency is equal to the electron acoustic wave plus this outgoing so-called Raman wave, the stimulated scattered wave, the Raman wave at that frequency. And the electron acoustic wave is at the plasma frequency. So this is going to cause a big shift. And this is our our dispersion diagram, frequency versus K. And it's shown both left and right propagating. And this is our electron acoustic dispersion relationship. And here are the electromagnetic waves. So the incident wave and the Raman wave. So the incident wave has to be, it turns out, well above the plasma frequency for this vector relationships to work. Has to be well above this, actually more than twice as high as the plasma frequency. And then the Raman frequency, it's still high, but you notice it's like the magnitude of the K vectors, it's a little bit more than half, maybe 2/3. So in frequency. So if the incoming wave was in the visible, this is more likely in the infrared, okay? Okay, and so that's a vector diagram. And this typically happens, it's hard to make these relationships, not hard. These relationships don't work for just any plasma frequency and any electron density. And this is a little bit more about that same process, the Raman scattering. It turns out that in simulations and in theory, it occurs at best at, or very close to, an electron density of the critical density over 4. So for light coming into a high density target, a microsphere that's ablating plasma, or even a thin film of metal or something like that that's ablating plasma, the light, as the light is propagating towards the critical surface where it's being absorbed, and eventually what's ever left at the critical surface will be reflected out. But before that, at a little bit lower density, the critical density over 4, is where this Raman process can take place. Okay, so here's relationships again, and this is in the book, so we don't really want to spend too much time going over this, but I just wanted to show you some of the numbers that come out of this analysis. It's a relatively simple analysis if you're into plasmas, but I assumed an electron temperature of 1 keV and a critical density, an electron density of critical over 4. And I went and I solved where did that conservation of energy and momentum work? How would it work? And so it turns out that the incident frequency has to be a little bit more than twice the plasma frequency. The electron acoustic wave frequency, well, that's also just about equal to omega p, and that's because this curve is so flat, actually. Okay, you can almost do that as a given. But when you solve these things, you say that the phase velocity, you'll find that for this wave, you solve for the different, the k vectors, and you'll find that the phase velocity of this wave, which is omega EA, electron acoustic wave frequency, over its wave number, KEA, turns out to be the following. Omega E, you find, is roughly omega P, and KEA has this. It turns out that the phase velocity of this electron acoustic wave that you've launched at high intensity is C over square root of 3. It's a gigantically fast wave. And if you, and it's a high amplitude wave. So the incoming laser wave, the examples that unfortunately experiments were done, many, the incoming wave is an intense infrared at 1.06 microns, neodymium, and focused down to intensities in the early experiments around 10 to the 15th watts per centimeter squared. It's into the place where nonlinearities matter a lot, and it's launching waves, which are seen in simulations, which are high amplitude. So they're high amplitude, high enough to trap innocent electrons, which happen to be moving nearby. And this wave, this crest of potential, of voltage really, is propagating at C over 3. So if you calculate what is the energy of an electron that's trapped in one of these waves and going at C over square root of 3, the calculation is that the energy, I think, was 120 keV. And there were other examples where you could get higher than that. But just for this calculation, it was 120 keV. And this is in a plasma that only has a 1 keV electron temperature. So this is a grand example. This and the Brillouin, and there are a couple others. There's another one called twice omega P instability. They've had their really strong effects. So you've heard me talk about the laser fusion, inertial confinement fusion at Lawrence Livermore and other places, and that's where this was all experienced. Unfortunately, if you to get fusion to work, you had to have intensities of greater than 10 to the 15th watts per centimeter squared. But when they went from lower intensity experiments, maybe 10 to the 14th, a few times 10 to the 14th, and then 10 to the 15th, all of a sudden, the plasma distribution measured was extraordinary. So there was the typical couple of hundred EV or 1 kilovolt emissions, both continuum and line emission. And then there was this amazing amount of radiation, really a lot, at very high energies. And so one question is, what's the threshold for these things? How do you get a handle on this? So these are two simple equations. One is, this is the oscillating velocity of an electron in an electric field. So this is your incoming radiation at 10 to the 15th had some electric field amplitude associated with it. With that, you get a velocity, oscillating velocity. And you might normalize that to get an index to the thermal electron velocity distribution. So if this oscillating velocity is small compared to the thermal, then the thermal processes are going to dominate. They're just, the plasma electrons in that case would be moving around in all directions, colliding, and on top of that, there'd be a slight modulation due to the laser field. So that would be down around 10 to the 13th or 10 to the 14th watts per centimeter squared. The electric fields would give this number, this index, this nonlinear index, V os over V thermal squared, and you just put these parameters in and then replace the E squared with an intensity over the speed of light, and the omega squared brings you a critical electron density, and you have the kappa T, and that's what this looks like. And if you just expand, replace the omega squared or the critical, that gets replaced by, for instance, it's easy to see here, the omega squared would be like a 1 over lambda squared. So, and the critical density would have that also. So this actually, leaving out all the other parameters, this nonlinear index is proportional to I lambda squared. So the intensity multiplied by the wavelength squared. And so we're going to see this again in a moment. If you keep this to much less than 1 by controlling the wavelength that you're using and the intensity, you don't see these stimulated Brillouin-Raman effects. So here are some experimental data. This is for a gold disc irradiated at 0.53 microns. And that's an interesting thing. Normally, you would have begun these experiments with 1 micron. Neodymium operates at 1.06 microns. And that's where these giant lasers at Livermore operate. But they can be frequency doubled and tripled, okay? And this experiment happens to be for the half wavelength, the frequency doubled. But this is showing, as a function of photon energy, how much radiated energy is there across this spectrum for different intensities. So for instance, for 10 to the 14th watts per centimeter squared, that index would be low, and you would have very little of these high energy photons. They're there, but they're quite small. But as you go up to near 10 to the 15th and above 10 to the 15th, the amount of radiation you have out at 100, where our calculation or estimate was, you've gained 1, 2, 3 orders of magnitude, okay? So that's one piece of data. Here's another one. This is going to show the I lambda squared. This is looking at a gold disk at 310 to the 14th. So these things are relatively low at 310 to the 14th. The index is relatively low, but you can see the lambda squared effect here. These are orders of magnitude. So there's a lot more relatively high energy. This one's 50 keV. It's high. We're going to see higher than that. But this is the infrared pulse itself. This is when it's been frequency doubled, and this is when it's been frequency tripled. And they do both of those. And in fact, I think most of the experiments now are done at the tripled, 347. And by the way, they're done at high efficiency. It is amazing how well you can convert 1 micron into the second harmonic. Numbers like 80% are realistic, even with giant lasers. And then mixing the 1 micron, the omega and the 2 omega to get 3 omega. So you actually have 2 crystals here, 1 crystal to get you to the doubled. And then after that, another crystal which mixes the continuing 1 micron omega and the continuing half micron. This is 1 omega and 2 to get 3 omega. And you still get really high conversion efficiencies. So how have they done? Oops. Oh, yeah, I was looking for one more slide. So here's something about how many superthermal X-rays are produced at these different wavelengths. So this is, again, superthermal X-ray conversion efficiency is written here, okay? And this is as a function of intensity. And so you can see when you're down around 10 to the 14th, you still have some issue in the with the driving 1 micron radiation, but it's really going very, very small when you double and triple. But when you get up to 10 to the 15th, you save yourself an order of magnitude, but at 10 to the 15th, you still have a problem. And unfortunately, with so-called direct drive, where the laser light is right on the target, you need to be up at least to 10 to the 15th, probably above that. And so this is this formula that we just saw before, that the nonlinear index is Vos over V thermal squared, I lambda squared. So at some intensity, this should have a sort of lambda squared behavior. So more between here and here than there is between here and there. So that's all I was going to say about that. It had a big impact on laser fusion, and yeah. Okay, any questions on that? I was going to switch topics for a moment. Okay. Oh, by the way, so for those who are working on Bella, it would be interesting in what is Vos over V thermal squared for Bella? Okay, so it's not that we expect there to be stimulated scattering, but this is a nonlinear index. Actually, it has other ramifications. But anyway, what would this be? What is kappa T for Bella? What kind of intensities are used? What does that mean? It must be a really big thing, because it's such a strong force at Bella, which is the effort to make a new accelerator based on plasma acceleration, how to get particles up to many GeV energies, so that potentially a new, very compact particle accelerator. But at any rate, the electron temperature is quite low and the intensities are high. And you in these situations, you can the incoming laser light can actually push the plasma completely out of the way. So for instance, I meant to put one of these slides. Oh, I know why I didn't do it. Anyway, I did experiments myself many years ago with laser light illuminating the microspheres or those lollipop discs and everything. And I did interferometry from the side so you could see the plasma evolution. And two things we saw was, one, that on axis, the plasma evolving, expanding away from the original surface was pushed in. Right at the critical surface, it suddenly sharpened up because the radiation pressure, what they call ponderomotive force, not a good name, I don't think, but at any rate, the radiation pressure was so strong that it actually pushes the plasma out of the way. And we had other ones where we look at these discs where if you know how to read the fringe patterns, you just look at them and you don't need to do Abel inversion. You just can see there is no plasma left in the middle of the target. It's just all been pushed out of the way. And that was at laser intensities a little bit less than 10 to the 15th, as I remember.
So Professor, I actually looked into this for Bella. And so our intensities are around like 10 to the 19 watts per centimeter squared.
I'm sorry, your intensities are 10 to the
19 watts per centimeter squared. Is that high? That might be off. Maybe
well, the ones I was talking about were 10 to the 14th to 10 to the 16th. 10 to the 19th, it depends on your units, but watts per centimeter squared.
I've
Seems a
seen.
little high, but I don't know the number.
Hmm.
Yeah.
But anyway, our electron temperature is around like 5 electron volts, so it's a pretty large. The value
Yeah.
nonlinearity comes out to be pretty large. So
Yeah. Right. Okay. You see, yeah. So it'd be worth rechecking. And I wonder, yeah.
So, so for I can't speak to petawatts since I work with some of the smaller lasers, but even for the 100 terawatt system, we're looking at laser intensity that focus 10 to the 18 watts per centimeter squared. So I have no trouble believing that the petawatt laser is kind of breaching that 10 to the 19 threshold.
Yeah, I see. So, so Josh, is that what kind of laser is used? Is it a petawatt laser?
yeah, it's a petawatt.
Oh, okay. I'm sorry. Or not sorry. Your number makes sense then. Okay, so thanks for the additional comment. Yeah. So so the Vos over V thermal, no wonder there are bubbles, where there's very little electron density in there, right? Yeah. So I haven't followed Bella and the evolution very carefully, but I hadn't in the publications I've looked, I hadn't seen anybody making this estimate, and it seemed like one to where maybe it's because it was so obvious. Yeah. Anyway, okay, so that's great, and thanks for the comments. Okay, so what I was going to do then is switch over. So this is a certain level of hot dense plasmas. Why do I say hot dense? Hot plasmas produce X-rays like magnetic fusion produces certainly hot plasmas, and they give a lot of X-rays off, but it's from a big machine. And so the density, when you couldn't use it for imaging experiments, it's just coming from such a large plasma. So we need hot, but we also need dense to get a very bright source of X-rays, which is of interest here. Okay, so these were all in general development, and then I've told you about EUV lithography, but EUV lithography was worked on in the early to mid 90s, getting up, I guess, around 2000 or something like that. And a lot of Berkeley students worked on it, by the way. In the class, it was a topic we talked about a lot. And a lot of students are now work in Silicon Valley. They got jobs. It was a little too early for EUV, but they knew a lot. And so there's a whole bunch of them who worked on EUV lithography, and many who took this class. But it stalled, and it stalled because the light source to produce the EUV, the magic 13.5 nanometer, where there were multi-layer coatings which could get to 70%, it stalled because there wasn't a powerful enough EUV source. And I think I'll show you a diagram in a moment about how there are these droplets of tin, or maybe a tin compound, but I think basically tin, little droplets of diameters around 30 microns, and they're coming down, and there's a CO2 laser which is putting out pulses just matched to them and hitting them and completely vaporizing them, and they produce a strong line emission from the tin ions, and that is the source. And there was a breakthrough in Taiwan at the company TSMC, led by a guy named Tony Yen, who now lives here and works in the Bay Area. And they made a breakthrough. Up till that time, the EUV sources, the laser-produced plasma, the tin droplets with CO2, were producing powers of like 10 watts, average powers of 10 watts. And it just wasn't enough. And so it wasn't considered a viable, it was considered, it would take a lot of work. And people were told, in fact, one friend at Intel would just keep telling people, 10 watts is not going to do it. 100 watts is not going to do it. But if you get to 100 watts, we'll take you serious, and we'll take the technology serious, and we'll see where we go from that. And so about 3 years ago, I think it is now, there was these experiments at TSMC, which involved the company Cymer, who makes the lasers, now owned by ASML, and together in experiments in Taiwan at TSMC, they suddenly made a breakthrough. And by the way, and remind me to tell you what the breakthrough was. And they went from 10 watts, actually 9 watts, up to 90 watts. And that was the breakthrough. And I think now they're up to several hundred watts, 200 watts, maybe they're even up to 300 watts. But when they went from the 9 watts to the 90 watts, there was an announcement in the newspapers that some unmentioned company had told ASML, the company who makes the steppers that print these patterns, and they use the Cymer laser in it. This unnamed company bought everything they could make for a year. I think the number was $1.1 billion they were paying. And I think these steppers, they're the ones, they have the optics and they have the source, they have the droplet, the CO2 laser, the droplets, all the optics and everything. And I'm forgetting what the scale is, but I think each one, and they're the size of a small bus, by the way. You know, and they have such incredible precision motions in them. It's a little bit amazing, but I think they sell, I won't mention the number. It's just such an incredibly high number. We used to say, oh, it's going to cost the price of a Mercedes-Benz. Forget a Mercedes-Benz. It's a fleet of Mercedes-Benz for each tool. And so Intel was the company, announced that it was going to spend something like $1 billion to buy everything ASML could make in a single year. And they got the ability to do that because they held really important IP patents. So now I'm going to tell you, we have some time, I'm going to tell you about the plasma story that goes with this. Oops, let me start here. So EUV lithography uses a CO2 laser at 10.6 microns. So it's a pulsed laser, okay? It irradiates small tin droplets to form an EUV plasma light source centered at 13.5 nanometers. The 13.5 nanometers is around 92 EV, and it is matched to the polysilicon multi-layer coating. That is the enabling technology. Without polysilicon, there's no EUV lithography. There's no other combination that comes even close. Okay, actually there is beryllium, but the beryllium nobody wants to work with because of hazards with the that result. There's a lung condition, berylliosis, that if you use beryllium. So that was no choice. But other than that, there's no other choice. So that's what's driving this whole thing. This is the early paper by Hiro Kinoshita in 1986 about, he wrote a paper about how you could do, he was working on so-called X-ray lithography, which is really, it's not contact print, but it's proximity printing, where you have a mask and you have a wafer and light comes in, X-rays come in around maybe 1.5 to 2 kilovolt. And this thing is so close, it just makes a shadowgram of it, but close enough that there's not too much blurring. Anyway, people had been working on that around the world, big thing here in the US and in Asia, and it was just failing. You couldn't make a big enough, it was a 1-to-1 magnification, which put a lot of stress on everything, and you couldn't keep it flat enough to avoid blurring. It wasn't going anyway. Kinoshita was working on it at NTT. It's like AT&T, but Japan, Nippon Telephone and Telegraph. Anyway, he was working on X-ray, and he, like many others, knew it just wasn't going anywhere. And he came up with this. He had read about 2 experiments. One, Jim Underwood, later at LBL, but not at the time, he and a guy named Troy Barbie, actually both of them were at Stanford. Jim Underwood and Troy Barbie. Barbie had this idea of making multi-layer coatings, not for EUV, but in the soft X-ray region, or just making them. And Underwood was an astronomer, and he suggested that they do a simple imaging experiment. They got it published in Nature, showing that you could actually image X-rays with optics. It was a simple two-bounce optical system. And so Kenoshita saw that article. And then later, Troy Barbie came up with a coating, which he accidentally found to some degree. He was still at Stanford, that combined molybdenum and silicon. And he was an expert. He was a world expert on making these different coatings, but he was just trying different materials. He tried it, and with friends found out that it could have an extremely high reflectivity. So Kenoshita saw those two papers, and he thought, well, it would be possible to make an entire EUV, what they call projection lithography, reduction projection. Now we've dropped all those words and replaced X-ray with EUV. But anyway, Kenoshita wrote an article. It's a lengthy article that showed all the major steps that would be needed to make lithography work. And he has a book out now. Yeah, this is his book. It's on Amazon. And it's only a year or two old. Anyway, so he was a major player. Kenoshita was a major player to tell the world, hey, there is a way to do this. Not everybody in the world believed this. In fact, Kenoshita said most people thought he was crazy. And for those of us who later worked on EUV lithography for a decade later, people still thought it was crazy. So, so some others, many people, truly many people contributed, but some of the interesting ones was Hans Hertz is a professor at KTH in Stockholm, and he started a company on EUV lithography, but he had the idea he knew about liquid jets and he knew about plasmas, and he was interested in X-ray microscopy, so he was using droplets for X-ray microscopy, but he saw that, okay, this would be a way to efficiently make the source without having excessive material, just little droplets. Because one of the problems is when you vaporize these little targets, these droplets that are coming down, a laser hits them and they vaporize, where does the vapor go? Where do all those ions go? And unfortunately, a lot of them wind up on your optic, your first optic, and it coats it and degrades the optic. So Hans Hertz had this idea, liquid jet laser plasma, extreme ultraviolet source, and he talks about the droplets. Okay, so he had several papers on that. And Martin Richardson then at the University of Central Florida also had the idea that actually using these little droplets and minimizing them, they called it limited mass targets or mass limited targets, again, to control the debris. So here's what the system looks like. So we've seen this before. If there was a person standing here, this is probably 6 foot tall right here, okay? So this is bigger. That's why I say it's the size of a small bus. And the CO2 laser is downstairs. It's too big to be incorporated in the bus. There's lots of stages that have to move. This is the optical system where you see yellow, or see here in violet. This optics is shown here. So let me go over briefly for you some of the components. One, it's a so-called step and scan system, which is shown here. This is what a wafer would look like, 300 millimeter silicon wafer. Do I have it? Can I open it? This is a silicon wafer. This is what they print computer chips on, okay? And it's super flat, and they put a coating on it, a so-called resist, a molecular, a system of molecules that when light shines on it, it breaks bonds, and you can make, you can fix it then, and you'll have a feature. So this is showing that on this 300 millimeter wafer, basically in this system, you print one field, maybe a centimeter by 2 centimeter, rough dimensions. You print one, you step to the other. That's why it's called step and scan. So you scan, you step to the next one, scan again, step, okay? And this is what they mean by scanning. The optics don't image. There's a mask pattern. Let me start with that. So the laser pulses down in the basement, comes up. There's some optics which take that radiation and shape it into a narrow curved slit of light radiation, which comes up and it hits a mask. So what is the mask? The mask is a pattern of, it's a flat substrate with a pattern on it, an absorbing pattern. Okay, so it has a molybdenum coating, so it will reflect. But on top of that, there's an absorber pattern, which looks like something like this. It's an electronic pattern for one layer of a computer chip. The computer chip will have nominally 20 layers, maybe a few more than 20 different layers to make a computer chip out of it, but you got to print each one. And so this thing will print, one of these machines will run for a day or two, just doing one layer over and over and over again, okay? So this is the so-called mask, which has the pattern that's to be replicated. The light pulses keep coming. There's a collection optics, which then images that onto a wafer, but to control aberrations in these very large optics, it only images in a slit. And so this thing gets scanned, the mask gets scanned along this way, the wafer gets scanned the other way, and this slit of illumination is scanned over the pattern here that's to be replicated and is reproduced down at the bottom, producing one of these rectangular areas, okay? And they're going to break them up later, and that's going to be one layer of a computer chip, okay? So they step and then they scan, then they step to the next one and scan another one, step to the next one, scan it. So it's called step and scan. Again, it's all of these optics are molybdenum, CO2 laser in the basement. This is the wavelength. The microspheres are about 30 microns, a little bit less than that, okay? And so it depends on this multi-layer coating that we learned about earlier, which gets a 70% reflectivity, but by the way, count how many optics there are here, right? The light comes in and the droplet is shown right here, tin droplet, okay? The light is, some light goes this way, it's lost. What's caught is about almost a hemisphere of collection optic here. Is the first optic, the second, the third, the fourth, the fifth. There's the mask itself, is the sixth, the seventh, the eighth, the ninth, the 10th, the 11th, the 12th. So it's around 12 reflections. So even though you're getting a 70% reflectivity, you got 12 different surfaces. So that's why you need a lot of laser power. That's why you need a lot of EUV power so that you can still produce an image on the mask, okay? And that was one of the novel things about EUV was that it required such a strong source because there were reflections off so many mirrors. Up to this time, the lithography was using optics, initially visible light, but later into the EUV before you fall off the cliff of absorption. But the optics have good AR anti-reflection coatings on them. So even though there was a lot of optics and a lot of surfaces, which are needed to control aberrations in imaging large areas. In fact, here, this is what the first optic looks like, the collection optic. You can see how big it is. Okay. And so the other mirrors, the other surfaces get a 70% or close to it reflectivity, but the first optic, the collector, is almost a hemisphere, 5 steradians. And so it's a little bit lower reflectivity. So here's the droplets. This is from Japan, from the company Gigaphoton. It's a competing company. It's not winning the competition, but it's been there. It does a great job. And this is showing some of the droplets. These are tin droplets coming down. Okay. There, it says here 28 microns in diameter. The laser pulses in this case is, well, it's 2 things. There's a neodymium pre-pulse at 1 micron. This is the pre-pulse. And then there's the main pulse comes the CO2 heating pulse, okay? And that's brought down to a focal spot of 80 microns. So this is 28 microns in diameter. Why 80 micron focal spot? Well, it's because this thing expands, okay? And actually, the expansion starts early by a pre-pulse. And the pre-pulse is there because for 2 things. Focusing a CO2 laser to smaller than 80 microns is really difficult. For high power CO2 laser pulse, you can't do it. This is what you can do. You can get to 80 microns, but to keep the debris of tin away, to minimize that being deposited on the optics, this diameter and the mass the number of tin atoms is kept to a minimum. So you need, when the CO2 pulse comes, it's got a bigger focal spot. You got to make this 28 micron target look bigger. And the way you do that is with a pre-pulse, okay? And the pre-pulse could be CO2 also. In fact, that is what ASML uses. ASML is the company providing all those big steppers. And that's what all the companies who are making these new computer chips, they all use CO2 heating, and they also use a CO2 pre-pulse, although that could change in the future to a neodymium pre-pulse. So Gigaphoton was always a leader in the use of pre-pulses. And it's one of your homework problems, by the way, is about a plasma expansion. It definitely relates to this, okay? And the great breakthrough that was made in Taiwan at the company TSMC, the great breakthrough was that they started using a pre-pulse. They had not been using a pre-pulse. It was a significant deficiency. But when they started using the pre-pulse and optimized it, that's when they went from their 9 watts to 90 watts of average power. Okay, so this is some of the parameters. Some of the parameters I know, some of the parameters I actually don't know well enough. And it's because the companies keep things close to their chest and you need a few more details. But anyway, here's what I think we do know. It's a CO2 laser at 10.6 microns. This is the average power level, although it's a pulsed laser. And the pulses are around 20 nanoseconds, but exactly how many, it's in black here because I don't actually know the number, okay? I have been told, it has been suggested to me that it's more than 10 nanometers, more than 10 nanosecond pulse duration, but maybe a few tens. I put 20. This is what I'm estimating is the energy per pulse. This is the frequency that they operate. For CO2 at this wavelength, this is the critical electron density. So light that gets into a density of, there's an expanding plasma around the tin where the tin droplet originally was, and it's going to be totally vaporized. But the plasma at the surface is more like 10 to the 23, 10 to the 24. And so when the CO2 pulse gets in to 10 to the 19th, whatever hasn't been absorbed by that point, it gets reflected. Another role of the pre-pulse is that it spreads out the plasma a little bit more gradually, and that makes for a more efficient absorption. So that also helped. So the pre-pulse not only makes the tin droplet bigger, but it also gives a more gentle plasma profile out towards the laser. You can make an estimate of the diameter of these things from these parameters, and it'll show you a number a little bit less than 30 microns in diameter. And in fact, what they use, I'm told, is like 27 microns. There is a pre-pulse, but what wavelength, it depends. One company is using neodymium, the other CO2, so the critical density changes. The pre-pulse has to come early enough for the plasma expansion to get a critical density out to 80 nanometers, because that's the match for the CO2 laser pulse illumination. So these are some of the conditions. The intensity of the laser, you can estimate, because you want approximately a 30 EV plasma. Why do you want a 30 EV plasma? Because the wavelength you want is 13.5 nanometers for the moly-silicon, which is around 92 EV. The peak of a black body is 2.8 kappa T. So if you had a black body of 30 EV, you would have a peak around 90 EV. That's why you want 30 EV. To get a black body at 30 EV, you need an intensity around 10 to the 11. So this is an example of using that black body just to get ballpark numbers, and they're perfect. They're absolutely perfect. Then you go into the lab and you try a little bit less, a little bit more, optimize it experimentally. So then this is just some more details. What do I want to say? So this is just some more details about the mask pattern, the resist, how big are the patterns. Oh yeah, those step and scan patterns. It's saying here that they're 26 millimeters by 33 millimeters, and you can put about 100 of those little rectangles on that big 300 millimeter wafer. Okay. And presently they're printing patterns which are in this ballpark, 13 to 25 nanometers half pitch. So, so the 13 nanometer wavelength is being used to print patterns which are sort of double or triple, okay? The name for this node, they call them nodes. The Moore's law is an observation that the ability to print computer chips improves every 2 years by decreasing the feature sizes by about 2 something, and that gives you, how many million transistors, etc. But anyway, it's called the 7 nanometer node, although the features are bigger than that. And this is just more of the same. This is an effort to estimate the 27 micron diameter of the tin, looking at how many tin atoms there were in this kind of diameter and how much energy there was coming in, etc. And the estimate wasn't so good, actually. It came out to 16 microns. So somehow or other, the number is bigger than that. And I actually don't know why. I just don't have good enough parameters on the focus intensity and the pre-pulse and how early is the pre-pulse. This is, I told you that simulations play an important role. This is the work of Professor Martin Richardson and his team, his graduate students at the University of Central Florida, where they did simulations of electron density versus distance away from the surface with a neodymium laser at 1.06 microns and a CO2 at 10.6. And by the way, the parameters that they used were shown here, an intensity of 10 to the 11th watts per centimeter squared. It's a perfect match for our 30 EV, okay? 30 EV, peak at 2.8, produce a plasma which peaks at 90, but of course it goes, it's a broad black body emission. But this is showing, for instance, the electron, here's the original surface, something times 10 to the 22 electrons per cubic centimeter at the surface, and then the laser light is coming in and ablating material off, and as a distance away from there, the electron density is dropping, but the electron temperature is increasing. Here they're showing, this is for, again, neodymium. The critical density for neodymium would be 10 to the 21. That's right here. And at that point, at that electron density, they're showing a temperature of a little bit above 30 eV, but the light is being absorbed all the way in at these lower densities. And again, these are lower intensities, 10 to the 11th watts per centimeter squared. So absolutely no nonlinear processes, okay? No stimulated scattering. This is a simulation that they did for CO2 illumination, which is what's actually used now in production, 10.6 micron CO2. In that case, the critical surface is at 10 to the 19th electrons per cubic centimeter. So right here, so the laser light can only get in to about right here. Okay, so the plasma blow-off is coming. And at that point here, the electron temperature, they're saying in this simulation, was about 40 eV, so a little bit higher than what we were estimating. But that's where you would, with your laser and your experiment, you would vary the intensity a little bit below, a little bit above, and see which one gives you a maximum number of EUV photons. This is showing the emission spectrum from tin and xenon, because xenon was looked at as a possible source, but it was so intense. Xenon was a perfect source. It would vaporize. You wouldn't be coating your optics like you would with tin. This is be inert, okay? But it turns out at its peak emission is a lot of line emission here, a gigantic number of lines, gigalines, okay? But it's around 11 nanometers, which is perfect for moly beryllium, but the companies all just decided that they did not want to deal with beryliosis threats, and so they went to tin at 13.5. That was their other choice. And there's a lot of emission lines. This is just the emission lines at 10 times ionized tin, but there's a lot of lines, but in fact, there's not just there's not only 10 times ionized tin, there's a lot of ionized tin. So this is also from Jerry Sullivan. The last slide was from his group, actually. It probably said from his group here, okay? But this is showing as a function of temperature, which line emissions will be strong, and this is in this band of 30 to 40 EV. And this is showing, for instance, here's the red line. This red line for 10 plus means you've stripped off 10 electrons. And for temperatures between 30 and 40 EV, this is what the dominant lines are. So if you're in this region of 30 EVs approximately, you're going to have 8 times ionized, 9 times, 10 times ionized, 11 times. They're all going to be there. And every one of them is producing a spectrum of lines. So it's a zoo of emission lines. And Jerry O'Sullivan was an astronomer who was working on EUV, and he was quite familiar with all of these, what do they call them? Doesn't have the right word I'm looking for. But anyway, he was an expert on all of this, but he was an EUV astronomer. But he and I sat next to each other at a meeting in Lund, Switzerland, which was covering a lot of different topics involving EUV. He was there for the astronomy, and I told him there was a community really waiting to hear from him. And he and his group got in it big time. And Intel Ireland, because they're from Dublin, funded them. So that was a happy story. So ASML is the Dutch company that made that small bus, which we call the scanner, sometimes called the stepper, okay? This is the ASML scanner. How many were being shipped? as a function of time. This is courtesy of the man I told you about, Tony Yen, who's currently at ASML, but he was a key person with this breakthrough on the power. And this is as a function of year. This is not power is it power in watts? Something's wrong here. It can't be power in watts. I think this is number shipped. This is number of shipped, and this is number of shipped with a power of 250 watts. But down here, that occurs. This is where everything changes around 2015. Actually, 2017 is when they broke through with the power. So yeah. So in this area here, in this time span here, they were around 9 watts. And then they jumped to 250 watts. And now I think probably by this year that they're certainly higher than that. So this is the EU. I should have put this slide earlier. This is just an enlarged view of how the step and scan works. I told you that there was a mask that has the electronic pattern on it, but there's a big substrate. It's 1/4 inch thick, 6 inches square. Low thermal expansion material, because there's going to be a lot of light hitting it and there's absorption. But there's a polysilicon coating here for reflection. So light that hits here or in the middle or here gets reflected off, but light that hits the absorption pattern is absorbed, and it doesn't. So now you need some optics to capture that outgoing wavefront, which has the information about what parts were absorbing and which weren't, and those optics capture this and bring it down to the wafer where you're going to expose it. Okay, so we're almost done. This is what a big issue is. Were there any defects in here? This is the perfect thing. Was there some little something or other here that's absorbing that wasn't supposed to absorb? Or was there worse? Was there something hidden in the multi-layer coating, maybe on the bottom? Maybe the bottom wasn't as flat as it was because there's a little speck of dust, a few nanometers in diameter was down here. And as a result, the multi-layer coatings all start, is like making a coating of snow over a rock. You know, when you get to the top, the rock is still, you can still see where it was. Those are called defects. And this is about defects on the top, which are easy to find. They're called amplitude defects, and defects at the bottom, phase defects. And in fact, checking on time, this is the first study of defect printability. So here, is a multi-layer mask with both an underlying defect pattern and a top side lines and spaces. So here's the lines and spaces at the top, but if you look, you'll see a faint cross here underneath and some other lines, okay? This is what it looked like in an SEM. This is what it looked like in an EUV experiment, exposure experiment. And this was quite interesting. These are the players. Con Nguyen was an EECS student. Now he's at Google. And he got the idea to do this. And he and Tai Nguyen, who was an actually was an MSE undergraduate, he was an AST student. The two of them made Con put up the underlaying pattern, the crosses and lines and dots on the mask, okay? And then Tai put a multi-layer polysilicon coating on top of it, and then Con went back and put the lines and spaces on top of that, and they went to print. And the question was, this pattern he put on the bottom, would it affect the printing of the pattern on the top? And it does. You could see where these different things were. So this was the first ever experiment on so-called defect printability. And it was done with that same Hiro Kanoshita, who was at NTT at the time, and his colleague, Tsuneyuki Haga. So the two of them had a beamline that would allow these EUV experiments at the so-called photon factory in Japan. And Con and I went there, and Con did these experiments. So that's a little bit about the mask and a little bit about the wafer. And remains a big issue for EUV. They've got to improve the way of finding defects, but this is also a big headway was made on this just a year ago. There's a Japanese company that makes an EUV source where you can look for defects in your mask before you spend a lot of time in the lab. And then there was this major breakthrough. I mean, basically Moore's law was not going up every 2 years. It had leveled off. It wasn't going anywhere. And EUV came to its rescue. The companies, both TSMC and Samsung, are using EUV to make these chips. They're putting enormous investments. This is a Samsung factory. These factories run, I forget how many billions. It's like $20 billion to build one of these factories. And they're building them both in Korea for Samsung, who makes its own chips and uses them in their own phones and their own pads. And also for TSMC, the same thing, making these same investments. And they, by the way, are the ones who supply the chips for chipsets. That's what they call them for the phones and the iPads. And I think Apple is supposed to announce later in April its new iPads. And for sure, their new iPads are going to be using EUV lithography. And by the way, the US is pressing all of these companies, Intel and TSMC and Samsung, to build factories. I think there are several being discussed for being built in Arizona. So why is this thing so slow? Well, so yeah. So this is a kind of old slide that they were going to ship EUV scanners in 2019. Well, they started in 2018. They put a lot of them out there in 2019. And in 2020, they were into high volume and lots of computer chips. And this is just something about Apple's new iPhones and what's the other one? And all the different companies using it. Oh yeah, so last year's class, one of the students, Joe Natal from the physics department, took the class, and he found this a nice video on YouTube. So if you want to see this, there's a good link here. And there are various articles that were good in 2019. I'm not sure if they're still live. Okay. Oh yeah, and so we were going to have in 2020, in February 2020, these were the kind of topics that we thought they would be discussing, and they were. And there was a reunion held for the people who played a major role back in the 90s and early 2000s. And so the president of ASML was there, a bunch of, we had, I think, wasn't quite 20 presentations, but you can find them. If you go to this website, you can find the presentations. And that ends our discussion of plasma physics for EUV lithography. And for the plasmas, any questions or comments? No. Okay. So next class, I gave you the homework problems, and Difan, I'm sure, will put it out there shortly, or anyway, the homework assignment will be out there shortly. But next class we'll start. I don't know if we'll have just one lecture or two, but the topic is EUV atomic lasers. They're made with plasmas. You're going to get photons in the EUV region. So if you're going to get photons in the EUV, that means the temperature must have been 30 EV or 40 EV, something like that. If you have a temperature of 30 EV or 40 EV, you got a plasma for sure. So to make a laser in the EUV, it's a plasma physics issue. Okay, so you got to know about lasers and plasmas. So there's a whole chapter on it. I'm not going to spend a lot of time on it because it's not one of the major technologies that we're using for anything. The power levels are too slow. The convenience is that you can make these lasers to operate in a university laboratory, but the power levels aren't that high. The pulse lengths are long, so they're not so good for the chemist. So basically, no one's really picked up on it, but it's nice physics. And I wanted to tell you a little bit about how lasers work, just so that everybody has a common understanding. And so for sure, that'll be the next lecture. Depending on how it goes, we'll say more. And then we'll have a lecture or two on optics and imaging. So imaging, normally I would spend a lot of time on that, but a lot of you are making presentations that involve imaging. So I'm not going to spend so much time on it. The optics, the main optics are the reflective optics at glancing incidence, which we've already discussed a lot. So I don't have to cover that. And maybe I'll just briefly show a few slides as reminders. But diffractive optics, so-called zone plates and gratings, that we haven't talked about so much. I'll show a little bit of that. And I don't know if one lecture is enough or 1.5 or 2, we'll see. If anyone has anything that they're particularly interested in that they want me to talk about, just send me an email on any of those topics, okay? So I think we are pretty much ready to go. Yeah. So I guess we just say goodbye and we'll see you on Thursday.
Thank you.
See you, bye.